We'll talk about an interesting topic about learning representations or learning latent interesting representation of the data. So the discussion will all be based on unsupervised learning, and we'll cover a couple of classic techniques for learning representations, namely PCA, principal component analysis, and also kernel PCA. And I'll just mention in one slide what ICA is, another common technique to learn structure. But it's a bit more advanced, so I'm not going to go through details there. OK, cool. So what's the motivation? Well, as I guess we all know by now, so the data these days, in the age of big data, we have massive amounts of data. And actually, not only we have massive amounts of data, many data points, but also in many interesting applications that the data is very high dimensional. Right? So actually, I have on my slides a couple of examples. Actually, these are even older examples, a couple of years old. So there could be even better examples these days. But OK, let me go through a couple of them. So for example, if we want to do document classification, we could use, say, the classic representation that you guys know, namely the bag of words representation, where for each word in the English dictionary, we have a feature. Right? So then we would have thousands of features. OK? But people that do natural language processing, namely NLP, they use even more features. So for example, it's also common to use the so-called bigrams, which means for every pair of possible adjacent words, we'll have a feature. Okay, and then we're going to mark down if that pair of adjacent words appear in our document and how many times, and so on. Right? If we use pairs, if we use bigrams as features, then suddenly we have millions of features. And even if we then augment with other type of contextual information, the data becomes even higher dimensional. Okay? So that's an example where the data is super high dimensional. Okay, another example. So some of you did the Netflix. Some of you are trying to do the Netflix for the project. And also, for example, in the recommender systems, and I'm sure this data is old by now, we could have at least 500,000 users, and they could rate, say, about 20,000 movies. So here you can think about having about 500,000 examples in 20,000 dimensions. Okay, so that's another example where the data is reasonably high dimensional. Or if you are doing, say, brain imaging, which is, for example, something that Tom Mitchell is doing, then you could potentially measure the brain activity in different locations in the brain, and you might be doing so at say, half a millisecond. Right? So then you get very high dimensional data. Okay? Or even the image data, right? If we have very high resolution image data, that's also very high dimensional. Okay, so basically today we have, in the modern age, basically we have massive amount of data, and often the data is really high dimensional. And so in this context, it's useful to try to learn some insightful but lower dimensional representation of the data. Okay, and this is exactly what we're going to talk about today. So the topics that we're going to cover today: PCA, kernel PCA, ICA. So these are powerful unsupervised learning techniques for extracting hidden, potentially lower dimensional structure from these high dimensional data sets. Okay, and why is it useful? Okay, why would this be useful? So I kind of implicitly mentioned why it's useful, but maybe do you guys want to volunteer to come up with a few reasons?
I think high dimension is hard to process and requires a lot of computation. But if you lower it to lower dimension, it will require less computation and perhaps a more meaningful representation of it.
Excellent. Okay, so and your name is?
Sean.
Sean. Okay, so Sean already came up with a great reason. Okay, cool. Other reasons? So one particular one that he mentioned is computation, right? So like it could be better use of resources, in particular running time, right? It could also be better use of other resources like memory, right? You requires, if you find a good lower dimensional representation, you need less running time. You can run a faster algorithm, right? And you need potentially less storage, more efficient memory from memory point of view, and so on. Yeah, other.
And the high dimensional data might be very sparse. It will be much harder to extract features from it.
Right, so it might be difficult to visualize or to understand. If it's very, very sparse, living in high dimensions, might be very, very difficult to make sense of it, okay? There are algorithms that do that, I should say. There is a whole literature called compressed sensing, or some other algorithms that we didn't talk about in the class, like Quino, and we do L1 regularization. So there are some algorithms that, for supervised classification, that are targeted to dealing with very high dimensional sparse data, yeah? There are some algorithms. But another approach is to somehow try to find the meaningful structure. The data is high dimensional and sparse. Maybe we can find first the meaningful structure and then run our favorite algorithms, right? So that's a different approach. Okay, yeah?
It's mentioned that we would extract some hidden structure from high dimensional data. What if there was like a good structure in the high dimensional data?
Yeah, we thought kernels do, right? I mean, so you could also go the other way around, yes. Yeah, but the topic today is to imagine that we live in very high dimensions and there is a good structure in a low dimensional data set. I mean, it could be as you are saying, it could be sometimes if you go higher, it's even better. Yeah, but the topic today is going in the other direction. But you are right, I mean, it's not universally true that if you project things, or if you, it's not universally true that in all data sets there is a nice, low, or hidden dimensional structure. But I'm just saying that in some data sets, in actually quite a few data sets, that's the case. Okay, cool. So let me also just basically summarize some of the reasons for which you want to do that, right? So, right, if we somehow are able to find insight, right, if we somehow live in very, very high dimensions, the data lives intrinsically in a very high dimensional space, but somehow there is a hidden lower dimensional structure, it might be useful to first recover the structure, potentially using unsupervised learning, and it might be useful for several reasons. So one of them is, as Sean mentioned, well, if we do so, when you can use more efficient, when you can where you can be more efficient from running time point of view, from memory point of view, right? All computational resources involved, even communication point of view, if we are in, say, distributed computing systems and so on, right? So basically, bottom line, we can make use more efficiently of the available computational resources. Okay, that's one main reason. Another reason, actually, maybe it can, and this is some reason that many people like, we can visualize better the data. Sometimes it's good to understand the data also. Yet another reason, actually, is, well, somehow if we manage to extract fewer dimensions that capture the data well, we might even also get a better generalization, better statistical properties. Because we often know, okay, very roughly speaking, that the number of samples we need might scale with the dimension. Okay, so that's another reason. And actually another reason actually is also sometimes when we apply some of these techniques, we eliminate noise. Because the data might be living in a low dimensional manifold, a linear subspace, but up to some noise. And somehow maybe after we do this, some of this dimensionality reduction or learning representation techniques, maybe we get rid of that noise. So everything becomes nicer. Okay, and right, in general, like many, if we do PCA, if we manage to do effectively PCA or ICA, then we get lower representations of the data, and in general, all the machine learning algorithms can be run more efficiently. Like we can learn clustering or regression or supervised classification more efficiently, right? Okay, so that's it's very useful to try to do so, basically. Lots of benefits. Okay, cool. Okay, and I'm going to go through the classic techniques for doing so, and actually PCA is maybe one of the most basic techniques for doing so. So it stands for principal component analysis, and I'm just going to have one slide, high-level description, and then I'm going to go through more details. So roughly speaking, what PCA or principal component analysis does, it's an unsupervised technique, so only uses unlabeled examples. And it's an unsupervised learning technique for extracting structure from a high-dimensional data set. And by structure, really, we mean variance structure. We want to find a low-dimensional subspace that captures as much as possible the variance or covariance information of the high-dimensional data. Okay? And so another way to say it, PCA is an orthogonal projection or transformation into a possibly lower-dimensional subspace, so that the variance of the projected data on that subspace is maximized out of all possible subspaces you might choose of the same dimension. Okay, so this is roughly speaking what PCA is. Okay, and let's go for a couple of examples. Okay, so for example, So let me go through the simplest possible example, which is this one here on the left. So here is an example where data lives in 2 dimensions, right? So intrinsically, so it's in 2 dimensions, and actually in those, so the first dimension is this one, it's the first feature, and this is the second feature. And you actually, as you can see here, basically the data is already intrinsically lower dimensional than the dimension of the ambient space. So in particular here, we can just really, only the first feature is relevant, right? The first feature already mostly captures most of the information, right? Because the second feature almost looks like noise, right? So here already one of the original features is a good feature, okay? And we might as well could keep that one, and we already have a lot of the information out there. Okay, so this is a simple case where basically the data is intrinsically low dimensional in the original representation. Okay, now a different case is the one on the right, where basically here in the original representation, right, if I look in the same, basically if I look in the same representation where I have the x-axis, the first feature, and the y-axis, the second feature, in the original representation looks like both features are relevant, they appear correlated, right, actually, right? But if we do rotate the data, right, if I rotate the data, and then if I basically rotate it, and from this picture I get it to this picture, right, if I just do a linear transformation or rotation, then I again get into a situation where only one coordinate is more important. Okay, or another way, if I look at it in this, even like without even rotating, if I look at it, well, there is this direction. It's not an original feature, but it's a direction, right? That again capture most of the information in the data, right? And only if I could find the direction and represent everything into that coordinate system, things would be easy. I would need just one number to kind of store each data point. Okay, so that's a picture. And so basically, this is exactly what so PCA is asking. So can we transform the features, the original features, so that, right, so for example, in this picture here, can we transform the original features so that after we do so, for example, here we only need one feature or one number to store each example. Okay, and more generally, what PCA is doing is finding a linear transformation so that in the new representation we have better structure, the data looks better. Okay, and more actually before becoming even more specific, let's look at a couple more examples. Okay. So here are a couple more examples. So here's another example here. So here, for my lecture, I'm going to denote by uppercase D the dimension of the ambient space where the data lies in. And lowercase d would be kind of the right dimension of the data in a certain sense. Okay, so here the ambient dimension is 2, right? But as you can see, basically the data is very close to a one-dimensional linear subspace here, right? It's very well represented by this direction, in this direction. Okay, or here in this second picture, the ambient dimension is 3, but actually the data is lies very close to a two-dimensional linear subspace. So right, kind of the intrinsic dimension is 2, not 3. Okay, so here basically in the first picture, the data lies close to a one-dimensional linear subspace, so it lies close to a line, because, yeah. And here the data, in the second picture, the data is very, very close to a two-dimensional linear subspace, namely a plane in this case. Right? And basically, as you can see in this picture, in these two pictures, in the case where the data lies on or near a lower dimensional subspace, say a lowercase dimensional subspace, linear subspace, then an effective representation of the data is to use the axes of those subspace, right? The axes that define those subspace. That would be an effective representation of the data. Like here, an effective representation of the data would be to just represent the points according to this direction, right? Or here, an effective representation of the data would be to represent basically the points according to the directions that define the subspace. Yeah, you guys have any questions? All right. Right, so in cases where the data lies on or near a low dimensional subspace, basically the axes of the subspace are typically an effective representation of the data, a more efficient representation. Okay, and so actually identifying the axes of that subspace is essentially what's known as principal component analysis. Okay, and this can be obtained by using algorithmically, this principal component analysis can be obtained by using some classic matrix computation tools like singular value decomposition or eigen decomposition. Okay, and I'll come back to this later. Okay, cool. Right. And as I already mentioned several times, what principal component analysis does is helping us to identify structure like this one here, and in particular, really, it is helping us to identify variance structure. That's the key object, covariance structure of the data. Okay, so let's go through. Let's now define what principal components are a little bit more formally. Okay. So basically the definition, the formal definition is that the principal components of the data are just orthogonal direction that capture most of the variance in the data. Okay, that's the formal definition. Okay, and let's think about the first principal component. Okay, and then we'll define the second one and then the third one and so on. Yes? Okay, so what's the first principal component? Well, it's the direction of greatest variability in the data. That's the definition. Okay, so for example, this here is the first principal component. Okay? And so, and another way to state it, or property of the first principal component, is that the projection of the data points along the first principal component discriminates the data the most along any one direction. So in other words, if we project the points into that direction, like this one here, the points are the more spread out compared to any other direction we could project the points on. Out of all possible directions we could project the points on the first principal component, the points are the most spread out. Okay? So that's basically the first principal component, the direction of highest variability in the data. Okay, and to make this a little bit more precise, so just a quick reminder, we've already seen this when we did the actually SVM, semi-supervised SVM, when we did perceptron. We've already seen this, but just to quickly remind you, right? So if we have a unit length vector v, like this vector v over here, right? Then, and if I have a point xi, just a data point, that in my lecture today lives in a uppercase d-dimensional space, right? Then the projection of my point xi onto the direction given by v is just the dot product of v and xi. It's the length of this segment over here, right? Lecture. It's so much better to have two screens. Last time I only had one screen, so I was forced to stay on that side of the room. It's so much better to be able to walk around. Okay, cool. So the first principal component is the direction of greatest variability in the data. Okay, and now how do we define the second principal component? Now the idea is that the second principal component is the next direction of greatest variability. Okay, now how do I formally define this? So what we're going to do, after we remove the variability in the first direction, then we find the next direction of greatest variability. Okay? And what do I mean by remove the variability in the first direction? I really mean by replacing each point. So my original point xi was this point over here, and I'm going to replace each point xi with the residual given by the first direction. Right? So, right, I'm going to, imagine that v is my first direction, right? Then v dot xi is the representation of a point in that direction. Right? And then what I'm going to do for each point x, I'm going to replace x by this residual, which is x minus v dot x, is a residual according to this first direction. Okay, so then I get a new set of data points, and then I find the direction of greatest variability in the data. Okay, that's the second principal component. This is mathematically what happens, and like in words, what this is, the second principal. So the first principal component is direction of greatest variability in the data. The second principal component is the next direction of greatest variability. And we'll set up the things so that these principal directions are actually orthogonal to each other. They are uncorrelated. Yeah, actually that's important. Right, so it's the next orthogonal, so the second principal component is the next orthogonal direction of greatest variability. Yes?
Orthogonality is an important condition?
Say it again?
Orthogonality?
Yeah, it's important. Yeah. So by PCA, we're going to define them, right? Because as I mentioned, if I went back to my picture here, it's very important. When I said that the principal components are basically the axes, right? In the case of the data lies, say, on a low-dimensional subspace, the principal components will be the axis of a subspace. And it's easiest to define axes by using orthogonal directions. Yeah, it's an important. We'll set up in PCA, we're going to make sure that they are orthogonal. And basically, when the features in the new representations become uncorrelated. That's the definition of PCA. In other techniques like ICA, actually, I'm not going to have time to, if I have time, I'm going to go through it. In ICA, we don't impose that. But in PCA, we impose that axes, the principal components are orthogonal. This is the way the things are set up. Okay, cool. So the first principal component is direction of greatest variability in the data here, right? In this example, this is the first principal component. The second principal component is a direction, the next orthogonal direction of greatest variability. In this picture here is this second component over here, right? And then so on. You can define the third principal component, the fourth principal component, and so on. Yes?
So when you say algorithm, will the algorithm just search for any possible orthogonal axis in the whole space and calculate and project every data point into the possible axis, and then calculate the projection and calculate the variability?
Yeah, so let me go more. Okay, so this is just kind of, I define mathematical what it is. Now, how do we find them algorithmically? This is what we are getting to, right? We're not going to do an exhaustive search. It turns out that there is a nice characterization of what these principal components are, and there are fast algorithms for doing so. Okay? And your name is?
Sure.
Well, nice to meet you, I guess. Okay, cool. Right, so actually to go back to your question, actually, so right, how do we, okay, so far I kind of just defined what they are in principle, but how do you compute them, okay? And in order to compute them, let me characterize them a little bit more, okay? Good. So, and actually in order to characterize them, okay, so I promise you that basically these principal components will be chosen so that they are orthogonal components. They're all going to have unit length, and they will all be orthogonal to each other, okay? This is the way we're going to set up things. Okay, and in order to characterize them, I'm going to assume that the data is centered, which mathematically just means I extracted the sample mean of the data from the data, right? So basically in this example here, I'll make this to be the origin. This point to be the origin, right? So we can always, given the data set, we can always just extract the mean from the data, and the data will be centered. The empirical mean from the data will be centered. Okay, now I'm going to denote by a matrix X, the matrix that will now be, I guess it will be D by N, so D is an uppercase D by N. So that in this matrix X, I'm going to stack together all the data points, right? So the first column is my first data point, the second column is my second data point, and so on. The nth column is my nth data points, right? So I have n data points as inputs. They all live in the uppercase D-dimensional space. And then I get this matrix X, which is just a matrix of size capital D by N, where each column is just a data point, right? Now, as I said, okay, let me try to understand a bit more what is the first principal component, yeah? And as already defined in the previous slides, what the first principal component is a vector where basically that maximizes the sample variance of the projected data, has the highest variability, which mathematically means just maximizes the sample variance of the projected data, right? So let me write this down, right? What is the sample variance of the projected data? Well, so because we center the data, basically maximizing the squares of the coordinates, right? So if this is my component, my first principal component V, right? Then if I project the data, the projected data will be V dot X on that component, right? And so then basically because I've centered the data, maximizing the sum of the squares of these coordinates in the new coordinate given by the direction V is equivalent to maximizing the variance in the direction, right? And so what we really want to do for the first principal component is to find the direction V for which this quantity over here, the variance, right, is maximized. The variance in the direction is maximized. That's mathematical what we want to find. Okay, and here I'm assuming, and I'll assume throughout the presentation that the data is centered. So I extracted the mean from the data. Right, so this is basically this is by now making everything more formal. This is exactly what I want to find. The first principal component is a vector that maximizes sample variance of the projected data. And now if I have a point X, then if I project it onto a direction given by a normal vector V, then the projection is already, we saw this in the previous slide, will be V dot X, right? And I want to maximize the variance over all my data points in the direction. And this is exactly this quantity over here. Okay? And it turns out that if I'm not going to go through the computation, but it turns out that I can just rewrite this quantity here, which is the average sample variance. I can just rewrite it as being V transpose, so given by a vector V, right? So given by a vector V, V is the direction here. When the average sample variance, which is exactly this quantity over here on the left, so the average sum of the squares of the coordinates in the direction, you can just verify, if you just expand this out, that this is identical to this quantity over here, which is V transpose multiplied V transpose, this is like now matrix multiplication to X transpose, again multiplied with V. So this is a matrix, these are matrix operations over here, right? So V transpose will be like a 1 by D, X itself will be, so this will be like 1 by D, right? V transpose, X itself will be D by, capital D by N, if you guys remember, right? Then will be N by D, and then again I'm going to have D by 1, right? So then at the end this is a number. Right? And you can just verify, and I'm going to go through the computation. It's an easy verification, but basically the sample variance in the direction V is identical to this quantity over here, V transpose X, X transpose V. Okay, this will turn out to be important to characterize what these principal components are, more algebraically. Okay, so basically what does it mean to find the first principal component? I just argue that finding the first principal component is equivalent to solving basically this optimization problem over here. Maximize, find the vector V of unit length, right? Such that this quantity over here, V transpose X, X transpose V, is maximized. Yeah, is this clear? And this identity over here can be easily verified by expanding out what this quantity is. Okay, so this is mathematically what essentially finding the first principal component looks like. Okay, now let's characterize it a little bit more, right? Because, right, what is actually the algorithm for finding it, right? So right now I'm just giving you a more mathematical characterization of the first principal component, but how do you find it algorithmically? And it turns out that actually if we just manipulate this, so this is what this is an optimization problem, right? It's actually a constrained optimization problem because I also want to impose the norm of V is 1, right? And why did I impose norm of V to be 1? Because, like, if you guys remember when I go back to my picture, so in this picture over here, the length of the projection of a point X onto a normal vector, onto direction given by normal vector V is V dot Xi, is the norm of V is 1, right? That's why when the norm of V is 1, this is exactly capturing what I want, right? Right, so when I need to impose here, I need to search for direction for a vector V of norm 1 so that this quantity over here is maximized, which is just basically the sample variance of the data projected on the direction given by V. And I want to maximize it because of the first principal component, this is what I need to do. Okay, now this is a constraint optimization problem. I want to understand this a little bit more. Okay, it turns out that it has a nice, there will be a nice characterization of these components, what they are. Okay, so because it's a constraint optimization problem, we didn't go through this in class, and I'm just going to quickly go through this now. It will take me because it's very easy, I'm just going to take me a couple of equations. I just want to mention at a high level how you can go from this constraint optimization problem to a nice characterization of V. Okay, now, because it's a constraint optimization problem, one way to deal with a constraint optimization problem is to look at the so-called Lagrangian. I think Kirsten went through this in the recitation, right? You did go through that in the recitation. For Lagrangian. Just the notion of Lagrangian, yeah, exactly. Right. In any case, this is something you are not required to know, but I just want to go through it briefly. Okay, so it's a constraint optimization problem, and so in order to solve it, we can turn it into an unconstrained optimization problem by basically wrapping up the constraints into the objective function. And how do we do it? We only have one constraint here, and what we do is just introduce a Lagrange multiplier. Lambda, and so now I'm going to try to maximize the function over V of the same original objective function minus something that has to do with the constraints, lambda V transpose times V. Which I should have had here minus 1 too, but it doesn't matter. So, yeah. So I wrap up the constraints into the objective function, and now it turns out I need to make sure that basically the gradient in the direction of V in order to do, when I want to maximize this function, this Lagrangian. And any vector V that maximizes the Lagrangian must satisfy the property that the gradient in the direction of V is set to 0, right? And if I compute the gradient here and use properties of gradient computations when I have matrix and vectors, then I get this equality over here. Because the gradient of this expression over here, V transpose X, X transpose V with respect to V, we just drop one of these guys. It will be X, X transpose V, just a matrix computation, okay? And the gradient of this guy with respect to V with a quadratic form will again just drop V transpose. Okay, so basically, if I set the gradient in the direction to v to be 0, then what do I get? I get this equality over here, which just says that basically, what do I get? I get that this is, by the way, the sample covariance matrix, if you wanted to think about it. So I get that XX transpose minus lambda, lambda is my Lagrange multiplier, times identity, minus lambda identity, all dot product by v is set to 0. Okay, but then if I solve for v, what do I get? I get, so if I rewrite this, what do I get? I get, yes?
What is the original dimension of
D, capital D, uppercase D, uppercase D. So the original one is uppercase D. So actually I have, actually I do have it. Original is uppercase D. Right, and so throughout the lecture, uppercase D from big is the original dimension, and lowercase d will be kind of the target dimension when I do PCA. Right, and because I'm only talking about one component here, this will be one, the target dimension. Right, so this slide perfectly captures, right? Original is uppercase d, lowercase d is a target dimension. Right, so if we go for this Lagrangian type of multipliers reasoning, we get that basically the first principal component must satisfy it's something interesting going on here. The first principal component must satisfy this equality over here, so which says that XX transpose, this is a sample covariance matrix, times V, this is like the direction I'm looking for, must equal to lambda V, lambda times Z, or lambda is, I guess, right, some quantity. Okay? And for those of you familiar with linear algebra, what is this implying? Yeah? V is an eigenvector of the sample covariance matrix, so it's implying, yeah? You are Sweta. Okay, good. Just to make sure, right. Sweta says basically what this implies, basically that, right, what this equality over here implies, what our reasoning implies is that basically the first principal component is an eigenvector. In particular, is the first eigenvector of the sample covariance matrix, right? Because if you think about it, XX transpose is the sample covariance matrix. Yes?
So why not just maximize the V transpose X transpose V over V transpose V?
Yeah, we can do that, but I'm now characterizing and I'm explaining to you what it means, right? So if it's good to understand what they are. Right, I mean, you could just, but because it turns out that this eigen, right, basically, at the end of my reasoning here, we're going to understand that these eigenvectors, we're going to understand that basically all the principal components are the eigenvectors of the sample covariance matrix. And if we know this already, then we can just use, standard eigenvector computation, right? We can just write two lines in MATLAB, and we get our principal components. I mean, of course, yeah, I mean, so this is, you could try to solve this optimization problem, but I mean, if we characterize it even better, it's only better. Yeah, but I mean, this is what basically the first principal component is. But getting some understanding helps us, yeah? Cool. So basically, as what I was saying, basically what we just argued is that basically the first principal component is really the first eigenvector of the sample covariance matrix XX transpose of the data points, right? And now we also want to think about, right, like the quantity that we really cared about, this was the sample variance, right? So if I have a direction V, what we really care about was the sample variance on the direction, right? Just this quantity, if you remember, so this quantity over here, right? So given a direction V, this was the variance in the direction when I project the data onto the direction, right? And I argue that this is the same as V transpose XX transpose V, right? So now I might, given the first principal component, I might also want to understand what is the variance, the sample variance into the direction. Okay, and by just using this formula over here, that basically the sample variance is V transpose X transpose V, yeah, just by using this fact, and using the characterization that we just got about the first principal component, what do we get? We can now compute the sample variance. Right? So the sample variance by definition in the direction is V transpose, XX transpose V. But what do we know about XX transpose V? What do we know about that? We just argued that this is the same as lambda V, right? So basically, if I, write the sample variance in the, of the projection, right? So if I say that this will be my direction V here, right? we just argue that the sample like in the previous slide, we argue that the sample variance into that projection, right? So if I go back, we just argue that this is a sample variance, which is identical to this quantity over here, right? And if I go back and compute it for my first principal component, right, what do I get? The sample variance of the projection onto that first principal component, like will be, say, this one here, will be what? V transpose X transpose V. But now I can just rewrite this. I can just compute it this way, right? I can just write this as being V transpose multiplied. So it's like a matrix multiplication, V transpose multiplied with X transpose V. But as Karen was mentioning, we just argued by using Lagrange multipliers that X transpose V is the same as lambda V. So then basically I can just rewrite this sample variance here as just being V transpose multiplied by X transpose V, which is the same as lambda V transpose V. But what do I know about V transpose V? 1, right? Because we said we pick V to be have length 1, right? Our principal components are orthonormal vectors essentially. They have all have length 1 and they have are perpendicular to each other, right? So that's 1. So then this is exactly lambda, right? So this, what I just argued is that the first principal component is actually the first eigenvector of the sample covariance matrix, and the sample variance of the projection into of the data into that direction, right? If I were to project the data into that direction and compute the sample variance of the projection, that's exactly equal to the first eigenvalue of the sample covariance matrix. Okay, so that's nice to know, right? Because we can just, I mean, once we know these things, we can just immediately compute the first principal component and the corresponding sample variance. Okay, so basically, you wanted to think about lambda, which is the first eigenvalue of the sample covariance matrix. So what lambda is, so the first eigenvalue of the sample covariance matrix exactly captures the amount of variability along the direction of the first principal component, right? Along the first principal eigenvector of the sample covariance matrix. Okay, and that people refer to this as the amount of energy in the direction, I guess, for natural reasons. Okay, so I mean that's cool because life is first. I mean they are nice objects, these principal components. Okay, and more generally, right? So we just argue that basically so the amount of variability in the direction given by the first principal component is exactly the largest eigenvalue of the sample covariance matrix. So in general, what we can do, we can just order the eigenvalues of the sample covariance matrix, right? Like maybe lambda 1 is the first one, lambda 2 is the second one, and so on. And then what we get, like after, basically based on a reasoning of this type, we get that basically the first principal component of my data is just the first eigenvector of the sample covariance matrix, and lambda 1 is, or the variability in the direction is basically just the first eigenvalue of the sample covariance matrix. Okay, then the second principal component will be the second eigenvector of the sample covariance matrix, we can argue, and then the amount of variability in the direction will be exactly lambda 2. Okay, and so on. Okay, so that's basically a nice characterization of what these components are. Right, and then so to answer your question, how do I compute, given a data set, how do I compute the principal components? I look at the sample covariance matrix, I compute the eigenvectors of the sample covariance matrix, and they will exactly be my principal components. And I can even compute the variance in the directions given by the eigenvectors, by the principal components by using the eigenvalues. Okay, so it has a very nice characterization. It's one of those dimensionality reduction techniques where you have closed form expression of what basically the axes in the new representations are. So that's really cool. Okay, for many of the other learning representation techniques, we don't have such beautiful, nice closed form expressions. Okay, probably this is one of the reasons for which PCA is so widely used, because it's easy to understand and it has a very nice and meaningful interpretation. Cool. Okay, so to summarize, basically, right. So what are the principal components? So basically, the principal components of the new axis of the representation are just the eigenvectors of the sample covariance matrix, X transpose. And because we picked because we actually picked the axes to be orthogonal to each other, in the new representations, the features are uncorrelated. Okay, and so basically, just to sum up, what is PCA is just a linear transformation, right? Because what did I do? I first entered the data, and then I just did a linear transformation, okay, to represent the data. Okay, so PCA is just it's a learning representation type of technique, also dimensionality reduction technique, if you want to think about it that way, where all we do, we just first center the data, extract the sample covariance, extract the sample mean of the data, to basically make the new sample mean to be 0, okay, and then we just do a linear transformation. And the linear transformation is exactly given by the eigenvectors of the sample covariance matrix. Okay, so it has very nice, simple characterization. Okay, cool. So that's, actually the way I described it so far is I described PCA, so PCA has two interpretations actually, it turns out. It has one learning representation interpretation and has one dimensionality reduction interpretation. Okay, and everything that I talked about so far is in the first interpretation. I described it as being a way to extract meaningful structure, to learn a cool new representation where I capture most of the covariance information. Yeah, so this is what I described so far, but it's good to also know the other interpretation. Yeah, you have a question?
So how do you show the eigenvector corresponding to the second eigenvalue is orthogonal to the first one?
We're going to pick it to be orthogonal. We're going to impose it. Oh, the second.
Yeah, so the second eigenvector
Yeah.
is orthogonal.
Yeah. By definition, it will be yes.
It should be.
Yes. Okay, so here is another interpretation of PCA, and this is as dimensionality reduction, right? So everything that we talked about so far is like what we said that PCA is basically when we do PCA, we are trying to find the linear subspace of a certain dimension, lowercase d was in my slide so far. I'm trying to find the linear subspace of dimension lowercase d, so that when I project the data onto that subspace, I have the maximum variance possible out of all lowercase d dimensional subspaces, right? I mean, I capture as much as the variance as possible out of all of those subspaces of the same dimension. As a target lowercase d dimension. Yeah, good. So this is the maximum variance subspace interpretation. But how about the? So here's another cool interpretation, as I said, which is like more like a dimensionality reduction interpretation. And so here's what it is. So another way you can argue that when we do PCA, we're going to find vectors. We're going to find axes, d axes, v1, v2, vd, so that when we project the data onto those axes, we minimize the reconstruction error. So the amount of loss in the when we do the projection is as small as possible. The square loss. So just to be clear here, we're going to think about the square loss. Okay, so PCA is always associated with square loss. Okay, so it turns out that we can argue that, right? So exactly. So actually, this right. That's basically what we can argue. Right. So in this picture over here, kind of the loss is really corresponds to kind of the length of this green part. Right. So there is this formula over here because when we talk about the loss, these are the coordinates in the original. So these are given a point xi. These are the coordinates in the new feature representation. If we represent according to according to the principal components, right? So for example, if I have just one, right, this will be the coordinate v dot xi is the coordinate of x on this new representation. But in order to talk about the error, I need to go back in the original representation, but I multiply by v again. Right? When I talk about reconstruction error, they have to be vectors in the same dimension. Okay. Okay. So actually, let's spend a couple more minutes on this. So basically, for simplicity, let's think about the first principal component. Right. So as we already mentioned, the first principal component in the first interpretation about learning representations. The first principal component was just the vector v, such that the projection of the data onto this vector captures the maximum variance of the data possible out of all possible one-dimensional projections. Okay. And I also want to argue now, I claim that actually one can show that first principal component vector v is also the vector v such that the projection of the data onto this vector v leads to the minimum reconstruction error possible according to L square loss, right? So, and again, the reconstruction error here would be basically, this is my original data point. If I project it onto the direction D, V dot xi is the coordinate into that representation. But in order to talk about the reconstruction error, I have to kind of move back this vector into the higher dimensional space, into into the two-dimensional space if I want so 2 dimensions to 1 dimension, so that's why I have to multiply by V here. This will be exactly the reconstruction error, and it really just corresponds to the length. So for a point xi, right, if I go back here, for a point xi, this quantity over here just corresponds to the length of the green part over here. Okay, and actually with this picture in mind, actually it's even simple to kind of see that I can almost argue by picture, and I'll try to convince you, that these two things are identical, right? Because what the picture says, right, so by using basically a Pythagorean theorem, I can just argue that basically maximizing the variance in this direction, so let's fix V, right, one dimension. I'm talking only about the first principal component. So maximize the variance in this direction, which it's equivalent to saying I want to maximize the length, the average square length of this blue component, maximize the variance in the direction, is I'm going to claim is kind of equivalent to minimizing the length of the green part, which is the reconstruction error, right? So basically, by just using the Pythagorean theorem, we can argue, okay, this is intuitively speaking, but you can make it formal. By using Pythagorean theorem, you can argue that basically these two viewpoints of PCA are equivalent, because maximize the variance in this direction corresponds to maximize the length of the blue part, yeah? Minimize the reconstruction error here, it's equivalent to minimizing the length of the green part, right? And we know that basically by the Pythagorean theorem, V squared, so the blue part squared plus the green part squared equals the black part squared. But the black part squared is the length of my examples, and that's fixed, right? And because that's fixed, right, if I maximize, and because maximize the blue part is essentially, because this is fixed, right, then I claim that because the blue part squared plus the green part squared equals this black part squared that is fixed, then this immediately implies that maximizing the variance in this direction, which is maximizing the length of the blue part squared, is equivalent to minimizing the green part squared, which is the reconstruction error. Yeah, just by picture, proof by picture, Pythagorean theorem, essentially. Okay, now you know the two viewpoints of PCA. One of them is just basically finding the subspace, a linear subspace that captures as much variance as possible in the data. And the other one is find the subspace, so that if I then project the data onto that subspace, I get the minimum reconstruction error possible. I lose as little as possible according to L square loss. Cool, so that's why actually these two viewpoints explain why, so you can think about PCA as both being a way to learn a representation of the data, useful representation of the data, and as a way to do dimensionality reduction, right? Because if the data is too high dimensional, for example, and you only can use so many dimensions for whatever reasons, for example, if you want to minimize the reconstruction error, if you care about, actually I have it here, the square loss, if you care the average square loss, but we just proved that the best way, the best subspace to project onto is the one given by the principal components. I mean, and for these reasons, actually PCA is widely used for dimensionality reduction. Like if you want to do image compression or many other applications. It's used for image compression, all sorts of compression problems. Actually, it's very commonly used in computer vision, actually. Like they always just, I mean, at least 10 years ago before, some years ago, before deep networks, okay. Now they have different ways to do, there is an alternative way to do all this, but anyway, it's still widely used, actually, right? So in computer vision has been very popular because the data is very high dimensional and often people just do PCA and then they run their favorite algorithms, supervised learning algorithms like regression and so on. Okay, so just basically to summarize some of these things about PCA. Right, so as we argued for the first principal component, basically, so the first principal component is basically the eigenvector, the first eigenvector corresponding to the sample covariance matrix, right? And then the amount of variability, the variance in the direction, the variance of the projected data in the direction is exactly captured by the first eigenvalue of the sample covariance matrix. It's also known as the amount of energy in the direction. Now, obviously, if we have 0 eigenvalues, at some point if we get 0 eigenvalues, right, then the 0 eigenvalues indicate no variability along those directions, right? So that means the data really lies in a lower dimensional subspace compared to the ambient space. And like, for example, if the rank of the covariance matrix, of the sample covariance matrix is k, we know that only the first k eigenvectors have no 0 eigenvalues. And so what we're obviously going to want to do, we want to only represent the data by using k axis, right? We're not going to, obviously, we're going to get rid of the eigenvectors with 0 eigenvalues. Okay? And so, right, in the original representation, basically, so, right, just to, again, to just write it visually, so data point, oh, yeah, so this should be an xi, upper script xi, right? It's a point xi, right? This should have been xi. It's a point, data point xi has d coordinates, uppercase d coordinates originally. Right, so it has, this is the original dimension. Right, I have d coordinates, and then if I do PCA, right, if I find the, say, the first d eigenvectors of the sample covariance matrix, this will be how I'm going to represent the data in the new axis, in the new representation, right? Or this will be the first coordinate of the data, right? As we argue, this is the length of the projection of the point, my point, onto the. So this will be, oh, it's something not, should x1, I. No, this should have been just xi, not xdi. Yeah, it should just be v dot xi. Yeah, I'm just taking I'm projecting the point. I'm just taking the length of the projection of my point into the direction. That's a typo there. Yeah, it should just be I'm just saying that this is how it look like. Okay? I'm just saying how you're going to represent the point. The point initially is d dimensions, right? And I'm just going to represent in the new feature according to the new coordinates. Now I have coordinates v1, v2, vd, v lowercase d, or these are new target dimension. And I'm just going to, the coordinate of in the new feature representation will be v1 dot xi. We argue that, right? It's the length of the projection of my point onto the direction v1, and so on, the length of the projection of my point xi into direction vd. So. This is the original representation, this is the new representation. And v is much smaller, lowercase d is much smaller, this could be much more efficient. Okay. And right, just to reiterate the point from the previous slide. Actually, right, it turns out, okay, this is not, so sometimes, even if the data is intrinsically higher dimension, it lives in high dimensional space, sometimes maybe the data lies near a low dimensional subspace. Not exactly on a dimensional subspace, but it could be very near a low dimensional subspace. And so, for example, if you plot the eigenvector, right, if you plot the eigenvalues of the sample covariance matrix, maybe some of them are really, really small. And the idea is that we can always ignore the very small ones. And if we ignore the very small ones, because the eigenvalues exactly captures the variability of the data in a certain direction, we are guaranteed that, well, we're going to lose some information, right? If we ignore the eigenvectors with very small eigenvalues of the sample covariance matrix, we're going to lose some information, but the loss in the information will be really small. So this is what people commonly do. They just put a threshold, and they just threshold all the eigenvalues that are below a certain threshold, and yeah. Cool. Let me see. Now, just to mention also, you might also be curious about an example. Actually, as I mentioned, PCA was very, very popular in computer vision. And so, actually, there is this seminal work by Turk and Pentland. I think they made New York Times because of that at the time in '91. So, New York Times wrote about their work. Right? So they showed that basically they took a data set, and then they kind of argued that for their application, they can just use, let's see, how many do I have here? I have 15 numbers, I think, right? Do I have? Are they 15? No. Yeah, there are 15 numbers. Okay, good, right. Because the first one is a sample. So they took faces, image. They took about 7,500 images, faces, and then they computed I guess the average. This was the average somehow, and then they computed the first 15 eigenvectors, Okay, and these are the first eigenvector, the second eigenvector, third eigenvector, and so on. Right? And then what they showed is that for many images, basically, so these are the first 15 eigenvectors. This is the sample average. And so basically, once you have these eigenvectors, you can then represent any image as a linear combination of these eigenvectors. So now you can represent any images by using 15 numbers. So the original dimension was very, very high because it was, I don't know exactly, but it must have been like at least a few hundreds. Right? It must have been like, I don't know, 64 by 64, right? Something like that. Right? So it was very high in the original pixel representation, but they did PCA with 15 components, and they showed that, oh, we can represent all these images by only using 15 numbers, and we don't lose much. Okay, so that was a very cool application. They made New York Times for that. It's an old example from '91, but it's the classic example. Yeah?
So you represent a base with 15 numbers, but there has to be some like metric to measure what you can do with these 15 numbers.
Yeah, it's exactly what we talked. The metric actually is the minimum reconstruction error. If we do so, like basically in terms of like out of all possible, if you use like if you want to only represent a face with 15 numbers, like if you want to find a 15-dimensional subspace, that's right. We know that PCA is the one that will give you the minimum reconstruction error. If you use a 15-dimensional subspace given by the PCA, out of all possible 15-dimensional subspace, that will be the one that has the minimum reconstruction error formally according to this. I mean, that's by mathematically, but I guess empirically they show that that's a good representation. I mean, they probably use it for all sorts. I mean, people use this for all sorts of, like, in computer vision, it's very common to just project the data into the subspace given by PCA, say maybe 50 numbers here, and then you can do clustering, you can do regression, you can do anything you want. Any classification or machine learning problem that you want to solve in the context of computer vision. Yes?
When you use PCA, I mean, it makes sense for images because the features don't necessarily mean anything, but you do seem to lose intuitiveness of each individual feature when you map it to this PCA dimension. So, I mean, are there any other applications where you can actually use PCA and not lose the understanding of your feature?
So why don't you lose the understanding of the features here?
Because you're mapping it to a dimension that you don't sort of understand. Right? I mean, it's now.
I mean, like here, they happen to, like in this visual stuff, it happened that these dimensions, like somehow, that maybe this corresponds to somebody with, let's see, glasses here or something, prototypical for somebody with glasses and so on, right? So here, actually, if you want, you can put some meaning around these kind of prototypical eigenvectors, right? Yeah, in vision, right? And you're asking, is it true the same happens in other applications? I bet that it happens, for example, in sound, speech processing. And also even in the, I think there's also been work, I think, in, I can point to you, I have to check. I'm pretty sure people also use for document understanding. Maybe like a new feature corresponds to some combination, minimum combination of the original features. There's something called latent semantic indexing, and I think that even there they capture some, like there was some interpretability. You're asking, basically what you are asking, if when I do PCA, right, do I have a nice interpretation of the new dimensions that I find? And you're saying here, are nicely observing that here that's the case, right? And I'm sure that in their work they mentioned this, that maybe this is a prototypical picture for somebody with glasses or something like that. Yeah, you're totally right. So you can interpret some of these directions somehow. And you're asking, does the same thing happen in other applications? And I think the answer is yes. I'm sure it happens in speech. It also probably happens in document understanding. And there is something called latent semantic indexing. And I'm sure that they discuss that. I'll point you to those papers. Yeah, that's a great point. I mean, like I guess one of the reasons that I mentioned at the beginning of my lecture, why do you want to do all these learning representations? One of the reasons was visualization, which people like to talk about. I mean, so, or like maybe interpretability is another one you're adding. Okay, cool. And I just want to mention, right, so this is the classic example from '91, but really it's a very common technique to do PCA and then to do your favorite algorithm. And actually we had an algorithm last year. I'm not going to go through the details here, but in any case, I had a NIPS paper last year of my students where I did distributed PCA actually. So, right, so here we assume that the data is on our machine, but what if the data is distributed across multiple machines? And then I want to find a common subspace that does all over the union of the data sets. Okay, so this is our modern research problem on PCA. Okay, and we had a very smart algorithm that did so. But anyway, so in the process of doing so, we then had to find out applications. Why do we want to do PCA, right? And so actually the applications that we had were we first did PCA, and then we did k-means clustering. And another application was we first did PCA, and then we did regression. Okay? And actually, in both cases, we observed, basically on real-world data sets like newsgroup data sets. So basically, for example, if you do k-means, so if your goal is to do k-means clustering, right? So basically, you can project the data on like a newsgroup data set. Basically, you can project the data onto something like 10 principal components. And then if you do clustering in the new projected space, you're going to do almost as well as if you did clustering in the higher dimensional space. But the running time is much, much better. Okay, so it's really useful, actually. Okay, and the same thing happens with regression and other learning tasks. So it's, it's really effective. And actually, for k-means clustering, I don't have it on my slides, but for k-means clustering, you can even prove formally. So not only you can show empirically, as I have here, but you can also prove formally for k-means clustering, if your goal is to do k-means clustering, which if you guys remember, say you are in a Euclidean space, right? And you want to do k-means clustering, if you remember, what is the k-means cost? So if I give you a clustering, what is the k-means cost of a clustering? So what is our goal when we do k-means clustering? Something we discussed last time. So we have as input a set of points, right? And then we have a target number of clusters k. And what do you want to do? Find a clustering that will have k clusters and also centers, right? And you want to minimize the sum of the square distances from each point to its corresponding center, right? So each point I find a clustering. With k clusters, I find centers for each of those clusters. Each point is assigned to its nearest center, right? We get Voronoi partitions, if you guys remember. And the objective function is I want to find the clusters and the centers so that I minimize the sum of the square distances of each point to its corresponding center. Yeah, so it's square distance. And because it's square distance, and if I go back here, like when I talked about the reconstruction error, so k-means cost is square distance based. And because PCA is also kind of square distance based, L squared, okay, then you can formally actually prove, and this was in our paper, that actually if you want to do k-means clustering, you can formally project the data onto a subspace given by the k over epsilon squared largest eigenvectors. And if you do so, you only lose 1 plus epsilon in the k-means cost. So provably, if you want to solve a k-means clustering problem, just do PCA first, project the data into the k over epsilon squared largest eigenvectors, you are guaranteed to not lose much. And you can do k-means clustering in the lower dimensional subspace, but this can be much, much faster. Okay? And so that's provably. And then you can also show that empirically, like you can show that this happens on real world data sets. Okay, so it's actually a very cool, useful thing to know. So somehow it's not widely known. Actually, this proof, so this is not proved due to me, but it's proved due to Dan Fellman. He had a course at a different technique to do dimensional reduction paper in SODA 2013, actually. So surprisingly, this was not known before. But I think it's a very useful fact to know. Because k-means clustering is probably the most widely used objective. And one can formally show, if you want to do k-means clustering, project the data onto the k over epsilon squared largest eigenvectors. So basically do PCA, find the k over epsilon squared largest eigenvectors of the sample covariance matrix, project the data there, you are guaranteed to not lose much. Just do k-means clustering there. So, as you can see, PCA is super useful. Okay, yeah, so these are plots for k-means, for clustering, and you can do, for regression, yeah. And by the way, there are all sorts of other clustering techniques, like in k-means we pick a center, right, in order to, and we want to minimize the sum of the square distances to that center. There is something called, very popular these days in machine learning, called subspace clustering, where the center, instead of being a point, is a subspace. And you can define, find the number of subspace, linear subspace, so that if you project the points into those subspace, you again minimize the sum of the square distances. And so actually this, the fact that you can also show that for subspace clustering actually, PCA is formally a good pre-processing technique. You can first again do PCA, keep only the k over epsilon square largest eigenvectors, and then directions, k over epsilon square largest directions, and then you are guaranteed to not lose much, and then you can do, say, subspace clustering, and then you do feature representation. Yeah?
So in this case, do you specify K first?
Yeah, you have to specify K first, yeah? But empirically, yeah, definitely you have to specify K first. Oh, yeah, to know where to project, sure. But, to get formal guarantees, right? But actually, empirically, for example, in this result, we just said, oh, I'm going to keep the first 5 components, if I keep maybe the first 10 components, and so on. And when I do k-means there for any value of k, and somehow I still want out, well, yes. Yeah?
Just one question. If we are talking about k-means clustering, I'm not sure if in the subspace we will get exactly k clusters. There might be lesser clusters than k.
Well, you can formally show, so that's exactly, so if you have, say that you have data living in any dimension, and if you want to do k-means clustering, well, one can formally show that if you project onto the k over epsilon square largest eigenvectors, in the new projective space, the optimal solution for k-means of k clusters is within 1 plus epsilon factor of the optimal solution with k clusters for k-means in the original space.
I'm just saying that the number of clusters might reduce. You have k.
Yeah, but the k-means cost is not going to change substantially. That's what I'm going to claim. So the number of clusters might reduce, but somehow the k-means cost. I mean, what do you mean might reduce? I can always split the cluster into two. I mean, you may say the number of natural classes. That's what they are formally, right? And given any data set, there is some well-defined notion of optimal k-means classes with any clusters. I'm not talking about natural or anything, but just find the k clusters. There's always an well-defined notion of k with k clusters, right? And that we guarantee that after you do the projection, the optimal k-means cost in the new projective space within 1 plus epsilon factor of the k-means cost of the original space. So I guess after all, I mean, probably, well, I guess what this implies is that basically it cannot change too much somehow the structure of the clusters, because like if it changed potentially, maybe. Okay, it's a good question. Yes? Yeah, don't go through them because they are in the distributed learning context. So I just wanted to show to you, right, so the details are, the 4 algorithms are like, I did not talk about them in course. All I wanted to show is that basically we can reduce the number of dimensions and not lose much information. Okay, we can talk about this offline, it's in my paper, but yeah. And by the way, these are all in the distributed learning context, so yeah. I just wanted to find some modern, like, because these techniques, like this is what everyone shows, but it's from 91, and I wanted to show you some more modern results, right, from last year. So I pulled them right before the class. Okay, and actually I'm going to skip this. So how do you compute these eigenvectors? Right, I mentioned that the principal component, the first principal component is the first eigenvector of the sample covariance matrix. You can do actually an iterative algorithm called the power method to compute it. Okay, and so you can show that basically you can start with any vector in RD, and then you can just iterate this process. Basically, you run the vector V through the sample covariance matrix, you scale it, and you repeat. And then you can formally argue that actually if you do so after so many rounds, you get a good vector that captures a lot of the variance that the first direction, principal direction has. Okay? And you can also argue you get a closing angle, actually. Okay, so there are known techniques for computing these eigenvectors. Okay, one of them is the power method. Another one is actually you can do eigendecomposition of the matrix A. And again, I'm going to skip this. So this is the point is anyway, you can just have a MATLAB function that will going to compute these eigenvectors for you. Okay. And actually, and again, I'm going to skip this too also because it will be on the slides. So doing an eigendecomposition of the sample covariance matrix, you can also do actually just an SVD of the original matrix, and you can argue that they are somehow related. Good. So, but in any case, there are ways to compute these eigenvectors, okay? Known ways to compute these eigenvectors. Okay, but, right, I also have a couple more topics that I want to cover, or one more topic at least. So let me just go at a high level. As a PCA is actually probably one of the most widely used techniques for learning representations or for doing dimensionality reductions. In this case, as we argued pictorially, they are very closely related, right? Which is nice. And it's nice because it has a very closed forms, like we understand what PCA does in a very closed form, right? We know that the first principal component is the first eigenvector of the sample covariance matrix. So we understand entirely what it is. Okay, cool. And you can use standard techniques for finding these eigenvectors, right? Requires actually, one nice feature requires no tuning of the parameters, right? It's just you get the sample covariance matrix, find the eigenvectors, you are done. It's nice, right? As opposed to other learning representation techniques, like deep learning and so on, where you have to tune the parameters heavily. Here, you can take it as a black box techniques, and often you're guaranteed to do well. Okay? Now, in terms of weaknesses, if you think about it, and has no local optima, you can solve it exactly. Cool. Yeah, so it's one of the few problems in machine learning where you don't have a local optima. Cool. So, but in terms of weaknesses, actually, it's limited to second order statistics. I've been talking throughout the lecture about the variance. We want to capture the covariance information, right? So it's limited to second order statistics. How about higher order moments, right? And also, it's really a linear projection, as I mentioned. We just do a linear projection to a low dimensional subspace. Okay, but sometimes a linear projection might not be sufficient, right? So what do we do? What did you say? Kernels. Cool. Kelly, yeah? You're Kelly. Cool. Excellent answer. Right, so one way to handle, as we know, I talked about this throughout the course, one way to handle nonlinearities, right, is to use kernel methods. Okay, so we can try to use kernel PCA. Okay, so what is kernel PCA? So, right, so in the principal component analysis case, we kind of, that does particularly well, PCA does particularly well if the data, so we have a data that lives in high dimensional the ambient subspace is high dimensional, but really it's kind of the data lives close to a linear subspace with high dimensional subspace, right? This one PCA does particularly well, okay? Now, when kernel PCA does well is if we have a kernel, and if we think about its phi space, right, the corresponding phi mapping, right? If you remember, a kernel has a phi mapping, right? Right? So that we never want to go very explicitly, but definitely a kernel has a phi mapping. So what is a kernel? Quick reminder. What is a kernel? It's a pairwise function that corresponds to mapping into high dimensional space, right? So that the kernel computation k of xy, that you can do it in the original space, corresponds to dot products into higher dimensional spaces, right? So kernel is basically just a function. Just a quick reminder. So what is a kernel? It's just a pairwise function with the property that k of x, it's basically a pairwise function, so that k of xy corresponds to phi of x dot phi of y, right? So the kernel has an implicit mapping phi into a higher dimensional space, okay? So that basically the kernel computation in the original space, I'm not sure what happens here, corresponds to a dot product into higher dimensional spaces, yeah? But the point is you never want to go very explicitly. Now, when kernel PCA are going to do well, if I have a kernel, so that if I think about what happens with the data into the phi space, right, I have the original data, and I'm thinking about what if I was to map the data into higher dimensional space, if I get into a situation so that in that higher dimensional space, now which can be very, very large, it can have many, many dimensions, but what if after I do the mapping, there is suddenly a nice linear subspace of that higher dimensional space, so that the data lies close to that linear subspace of that higher dimensional space. Okay? If that's the case, then this is when kernel PCA will do well. Right? So basically, the data might not be close to a linear subspace in the original representation, but it might be close to a linear subspace of the phi space corresponding to my kernel. If so, then I can just apply kernel PCA. Okay, and I have slides. I'm not going to have time to go through them right now because I'm out of time, but just I want to mention that it's, while some of the arguments are obvious to kernelize, kernel PCA is not tricky to kernelize, but does require a little bit of thinking. And in particular, like if you remember, when we compute, we said, well, the first eigenvector, so the first principal component, right, corresponding to the eigenvector is the first eigenvector of the sample covariance matrix. So in order to, the sample covariance matrix was a matrix X transpose, and actually this was a D by D matrix, right? So, and the entries don't correspond to dot product into higher dimensional space. And really the matrix that I want to use is X transpose X, because if I have X transpose X, that corresponds to kind of dot product of the original examples. Okay, so then you have to do a little bit of, right, so if you just look at it, the first look, you might say, oh, I have XX transpose, a sample covariance matrix, D by D does not involve dot products between examples. So you know, it's not obvious how to kernelize it. But then if you just do a little bit of rewriting, you can basically just rewrite, you can go for some little bit of computations and just use properties of what the first principal component is and so on. And then you can just notice that you can do everything in terms of X transpose X itself. Okay, so then I'll have this on the slides, but the whole point is that you can rewrite everything so that it's in terms of X transpose X, but X transpose X exactly corresponds to the matrix of dot products between examples, so then I can just kernelize it. I can replace X transpose X with the kernel matrix. Okay, and then I can kernelize it, and then I do great. Okay, So this will be on the slides. I mean, if you're curious to go through the example. Right? The point is that you can kernelize it. Okay, cool. And I'm not going to have time to go through ICA. I'll just put it as additional information if you guys want to look at it. But okay, just to summarize. Okay, so PCA is probably one of the most widely used techniques for doing both learning representations and dimensionality reductions. It's a nice technique because we understand it very well. Yeah, it has a nice closed form expression. We can find the principal components nicely by using an eigen computation or singular value computation. And it's widely used, and you can kernelize it too, to help handle nonlinear structure too. Okay, cool. So questions? All right.